Serkan, off you go.
All right. Welcome to my talk. I'm Serkan, and this is a joint work with Philipp, Michel, and Jonathan. And I will talk about multiple resumptions and local mutable state in the context of effect handlers and the effect programming language. First of all, what are effect handlers? Operationally, you can think of effect handlers as a more general form of exception handlers, where the handler is able to resume computation from where the effect was performed. We have multiple options here. The handler either does not resume. In that case, it behaves just like an exception handler, or it can resume once. We also call that a single shot handler, and that allows you to model stuff like coroutines and generators in your program. But you can also resume multiple times, and this allows to do really cool stuff like non-determinism and backtracking, logic programming, a lot of stuff. Right, but multiple resumptions are usually believed to be very inefficient to implement, and there are languages out there that explicitly disallow multiple resumptions to remain in the more efficient world. Also, multiple multi-shot handlers make it more challenging to support local mutable state efficiently. And then in this talk, I will present the compilation of the effect language that supports multi-shot handlers and local mutable state, while keeping a constant time overhead for single shot handlers, which are the most common form of effect handlers. Okay, let's first look at a few examples. Effect handlers first need effect operations, and this is how a signature of an effect operation can look like. In this example, emit takes an integer argument and returns unit, and is used to emit values like in a generator. And this operation can then be used in this example range, where we are emitting all the values in a range between two integers. And note that the function itself returns unit and only produces the values through this effect operation. And to actually call the range function, we need to provide a handler. And this can look like this. Here we have a sum function that takes an emitting program and wraps a handler around it by first allocating an accumulator, initializing it to 0. Note that this is a mutable variable. Then it installs a handler where it runs the program and returns the current state of the accumulator. And the handler takes care of adding the value to the accumulator and resuming with unit. And if we now call sum on the range of 1 to 5, we get the output 10 as expected. Here's an example that uses multi-shot effect handlers. We have an effect operation flip that returns a Boolean value which can be used for non-deterministic computation. And the handler for flip wraps the given program in a singleton list, and the handler then resumes twice, once with true and once with false, and also concatenates the resulting lists. Basically, this handler goes through all possible paths and collects all the possible outcomes. Now, what happens if we use multiple effects? In this example, we are first emitting 10 and then do a coin flip, and depending on the result, we emit either 1 or 2. We can compose our handlers from before by first gathering well, first traversing all the possible paths, and then summing up all the emitted values. And that would output the value 13. But we can also handle the effects in the opposite order. In that case, we collect all the possible sums on each possible trace. And that would give us the list of 11 and 12. It's important to note here that the handler sum it also includes a mutable variable, and the state of that variable is resetted whenever the handler for gather resumes. Otherwise, we wouldn't get the desired output here. Now, what do we need to implement effect handlers? We need a few basic operations for that. We need to be able to enter a new context, and we need to be able to exit that context and take a snapshot of it, or to capture the continuation there. And we need to be able to restore this snapshot and continue the computation. For that, we're using a few operations known from multi-prompt delimited control. First of all, we are having the reset operation, which on this abstract call stack here just pushes a delimiter or prompt onto the stack with a freshly generated label. Also, in the environment, we're storing this fresh label in the variable p. Then we can, after we've built up stuff on the call stack, we can shift to the label that we've captured earlier. And that would include looking for this label in the call stack, and then taking it all off from the stack and storing it in the variable k. Finally, we have the resume operation, which takes such a captured continuation and pushes it back onto the stack. It's important to note here that k remains in the environment and might be used again. That's how multi-shot effect handlers work. It's also important to note here that there might be mutable variables within this k, which keep their state at the captured point. Now, to implement these three operations, we have a few challenges we want to address. First, we want to avoid traversing through the stack and looking for a label. This problem has already been solved for single-shot handlers by this paper, Lexical Effect Handlers Directly, where it was shown that we can use direct pointers to the delimiters for lexical effect handlers. And we are generalizing their approach to also work with multi-shot handlers. Second, we want to avoid copying continuations in the case of single-shot handlers. And for that, we are relying on our memory management technique, which is garbage-free reference counting. This provides us during runtime with a count of how many references we are having to a continuation. And then we only copy if we have more than one reference. Finally, we also want to avoid traversing a continuation when we are resuming them in the case of single-shot handlers. And for that, we introduce a notion of valid and invalid continuations that differentiate those that can be resumed in constant time from those that need to be adjusted first. Now, how does all of this look? It all boils down to how we represent the call stack that we've seen earlier in memory. Instead of one stack, we are using a linked list of stacks, which we also call the meta stack. And instead of maintaining a stack pointer, we're maintaining a meta stack pointer, which is this MSP here. Also, each stack is paired with a separately allocated prompt, which represents these delimiters on the left side. The delimiters themselves are not included in the call stacks themselves. Right, and finally, if we have a label on the left side, this p equals number 1, we instead store a pointer to this prompt 1 here. That also means that the label itself is actually not included in the low-level representation. Now, in this setting, if we want to enter a new context, or if you execute reset, we just allocate a new stack and a new prompt, and link it to the meta stack. Also updating the meta stack pointer. Then, if you want to execute shift, we're passing a pointer to the desired prompt. So the prompt itself might be arbitrarily deep in the meta stack, but that doesn't matter since we are having a direct pointer to it. From there, we go to this next state where we update the meta stack pointer to the next stack in the chain, which is after p. Also, we take the stack of p and link it back to the first stack from before. And that way, we can just return a pointer to this last stack and also have a constant time access to the first stack. And if you only had single shard handlers, then we could just reverse this operation to resume a captured continuation. But since we also have multi-shot handlers, there are a few things to consider first. First, we need to see whether we need to copy the continuation. For that, we look at the reference counter of the stack, and if it is 0, meaning that there are no other references to this, then we know that we don't have to copy it. Otherwise, if it is not 0, then we must copy. And how does copying look like? If we copy a stack, the copy still points to the same prompt as before. But this introduces a problem because the prompt can only point to one stack at a time. And we are calling the stack that is pointed to by the prompt valid stack, and the other one invalid. And we also introduce an invariant at this point, that the meta stack may only contain valid stacks. Now, with that, we can copy a whole continuation by copying each stack individually. But now, of course, we cannot resume the copy because these stacks are all invalid. Now, if we want to resume in a possibly invalid continuation, we first have to revalidate all the stacks. And for that, the straightforward approach would be to just iterate through all of the stacks and to redirect the prompts individually. But of course, we're having the goal of constant time resumption for single shot handlers. So we need a way to check in constant time whether we need to revalidate anything. Because as we've seen earlier, the shift operation keeps the prompts all in a valid state. And they might still are. For that, we introduce another invariant here. Stacks in a continuation are either all valid or all invalid. And that way, we can check the validity of a continuation by just looking at one stack. And of course, when we have an invariant, we have to maintain it somehow. In this case, whenever we revalidate a stack, that might invalidate other stacks because we are redirecting the pointers around. And in that case, we have to invalidate the whole continuation that the stack was part of. Right, to summarize, resuming is done in 3 steps. First, we look at the reference count and copy if needed. And then we check the validity of a continuation and then revalidate if needed. And finally, we link the continuation back to the meta stack. And all of these steps are always, the 2 checks we're having here are always succeeding for single-shot handlers, because for single-shot handlers, we are never copying anything. And if we never copy, we also never get invalid stacks. Right. Also, one more thing to mention here, the implementation of mutable state is very straightforward in this setting. We can just allocate the variable onto the stack, and as a reference, we can not store the direct pointer to it, but we are storing a pair of a prompt pointer and the offset within the stack. And that allows us to reference this variable later by just adding the offset to the stack address. Great. Now we have implemented this compiler in the LLVM backend of Effect. And for that, we also ran a bunch of benchmarks. We're using a set of benchmarks that are explicitly designed to measure effect handlers in many different languages. We're comparing here to Lexa, OCaml, Coca, and F, and also the old Milton backend of Effect, which is now deprecated. On this plot, you can see the relative performance of the other languages normalized to the performance of Effect. Bars that go up are faster than Effect, and bars that go down are slower. You can see that in most cases we are pretty fast. A lot of downgoing bars here. And there's also the differentiation here between lexical and dynamic effect handlers. The lexicals are represented here in orange and the dynamic ones in blue. And we have one special benchmark here, checkpointing, which we added separately to the set of benchmarks. This benchmark is specifically designed to rely on both multiple resumptions and local mutable state. And this is not supported by both Lexa and OCaml. So that's why we're having a bunch of X's here. And we could only run this example on Coca, which performs a lot worse than Effect. Also, we are you're seeing the geomean here, so the geometric mean of all the other benchmarks. And as you can see, we're performing relatively well, while having a language that is more expressive than others. Right, there's still one limitation in our implementation. The prompts that we've seen can always only point to one stack at a time. And that means that the meta stack can never contain multiple stacks that share a prompt. On the source language, that means that we can resume multiple times, but we cannot resume a second time while the first resumption is still running. And this means that we can do the 2 resumptions on the left side, but on the right side we are seeing what's called bidirectional handlers. That means just that we're resuming and immediately resuming again, and that is not allowed in our runtime. Right. To conclude, we have a language with multi-shot handlers and local mutable state, and we have constant time continuation capture and resumption for single-shot handlers. And we have a constant time access to mutable variables. In the paper, you can also find a formalized intermediate representation with the semantics on a stack-based abstract machine, and a full translation to an idealized assembly language. And with that, thank you for your attention, and I'd be happy to answer any questions.
Kimio, the second last slide about not being able to resume inside a resumption. Can you say something about types? Do you have a type system that doesn't allow that? I mean, what happens when you do actually have such code? It just blows up in runtime.
We don't have a static guarantee that exclude these cases, but we do have we can detect this during runtime, and in that case we just abort the computation and panic.
So you detect it during runtime?
Yeah.
Hello, I have two questions, actually more to test my understanding. One, when you say mutable state, if you resume a thing multiple times, do you reset all the mutable state? Does it look like all the mutable state is reset?
Can you repeat that? Sorry.
So suppose you have a counter that counts how often you have emitted. Yeah. And if you resume it multiple times, does the counter get reset to whenever you created it? Okay, that's how, but can you do the other multiple state that basically has a global counter, for example? Could you do that in your system? I don't know if it's useful or just...
I'm sorry, I think
suppose I wanted a global counter that doesn't get reset as a mutable state.
Counters reset whenever we resume.
When you resume, yeah.
Yeah, if we resume 10 times, the counters reset 10 times.
Yeah. My question was, can you make one that doesn't get reset in your system?
Only if the state is captured by the handler. If this state is allocated outside the handler, then
that makes sense.
It is not resetted.
Okay, and one tiny other question is, you're doing the illusion of copying if there's the reference count is like basically there's only one reference. I think, or just my question is basically, does it save more than a constant factor in runtime? I assume it does, but I don't know. Like if you instead did always copied, you didn't do the reference counting check, you always did the copy, would it slow down your program by more than a constant factor? Like you have this clever thing where you check how many references do I have and then I don't copy. How bad, if you didn't have the check, how bad would it be?
I'm sorry, can you repeat the question?
Okay, so you have this reference counting. You don't do a copy if you only have one reference in your program to it. And my understanding is that this one saves a lot of time and it basically saves arbitrary amounts of time, but my suspicion is that it may only save you constant factor. Like it only makes the program twice faster or 3 times, no matter what. But I don't know if that's true. I assume it probably makes a program instead of quadratic runtime, you can have linear runtime or something.
Yeah, I mean, if we have to copy, this would not be constant time at all, right? It would scale with the size of the continuation.
And that can get arbitrarily large at runtime?
Yes.
Okay, if you have a deeply nested thing. Okay, yeah, thanks.
Any other questions? I had a question. So your restriction means that I cannot run these things in parallel, right? I would like to run these continuations, like copy them multiple resumptions on multiple cores in parallel. So your restriction where you had in the last slide, that would mean that I cannot use the system for parallel programming, right? I have a continuation. I want the same continuation to explore false on one core and true on the other core, where you had this flip example.
Well, in the flip example, the first resumption is done computing when the second resumption is executed, right? So that is not that's not a problem with our limitation. And in fact, we have never really encountered the limitation in practice, even though we have a lot of examples with thousands of lines of code.
But is the effect a parallel language? Does it execute things in parallel at all? Effect language.
Parallel. execution. No, we don't have that.
Cool. All right. Any other questions? No? All right, let's thank the speaker again.